Hello everyone. Welcome back to Virtual Learning with Mr. Khan. We are going to start a brand new unit today. We are starting a brand new quarter today. Lots of exciting stuff. You've been with me / your other teachers on Microsoft Teams for the past 2 weeks now. So hopefully you feel totally comfortable with just kind of the setup of class, what you're expected to do, what your weekly responsibilities are for me. Hopefully you're good with that stuff, and now we can fully focus on just learning math moving forward. This lecture expected again to be about an hour long or so. You need to watch the entire video, take notes on it because it will help you with both your classwork and your homework. So let's get started. First of all, welcome to Unit 8, Rational Functions. We are at the start of a new unit. We are not talking about radicals anymore. I mean, they'll pop up, but our focus is now on rational functions. We are going to be covering this for this week and next week. Before we get to that, let me just talk about some announcements first, okay? First of all, this is the first week of quarter 4. So start off strong by getting your classwork and your homework completed on time. Both assignments, both Khan Academy and that Microsoft Word document, are due on Friday again at 11:59. Those will be your first grades of quarter 4. We have 5 objectives today, and they are listed on your screen here. You can pause the video if you want to write those down. All right, so intro to Unit 8. First of all, Unit 8 is called Rational Functions, so you need to understand what that is, right? What is a rational function? A rational function is a ratio of 2 polynomials, or in other words, a fraction with a polynomial on top and a polynomial on bottom. And you can see some examples shown below, okay? So f of x, or just y, equals 1 over x. 1 is a polynomial, x is a polynomial, so 1 over x is called a rational function. But they can be more complicated than just 1 over x, right? We could have x squared plus 2 over x minus 1. Or we could have x minus 3 over x squared plus 2x minus 5. Or we could get really, really crazy and we could start throwing degrees of 5 or 6 into those polynomials. Let me show you a few of these graphs so you can see what they look like. And I'm going to set this up so that I don't have to keep doing this every time. There we go. Now you can see me and you can see the PowerPoint over here. Okay, so I wanted to show a few of these rational functions to you. So over here we have y equals 1 over x. Let's click this and see what it looks like. Yikes. So it looks like 2 different functions here, but it's actually not. It's just one function. If we plot 1 over x, and we plot the y values that correspond with that, this is what we are going to get as a result. This is called an inverse variation, and we will talk soon more about that specifically, what an inverse variation is. Let's go over a few more of these examples. X squared plus 2 over x minus 1 looks like this. Let me zoom out a bit. Almost looks like a Nike swoop a little bit. Getting a little bit crazier. X minus 3 over x squared plus 2x minus 5. This looks like it has 3 separate parts to it. A really, really strange rational function. You can see that we have this like lopsided parabola in the middle here, followed with these, or surrounded by these 2 curves. And then just for fun, this wasn't on the PowerPoint slide, but you can see this here, this crazy polynomial on the left side of your screen. Let's see what this looks like. This is another example of a rational function. How strange, right? Listen, y'all, the higher the degree, meaning the higher the exponents on the top or the bottom of your rational function, the more complicated your graph is going to be. So you can see over here on the left-hand side, we have x to the 5th, the degree of 5 on top, and the degree of 6 on bottom, x to the 6th. So if we graph a rational function like this, it's going to get pretty weird. And you can see it looks very strange, especially in this middle section. And then it like dips all the way down to like negative 68 or something like that down here. It's pretty strange. So anyways, those are examples of rational function graphs. Later on in the presentation, we're going to focus on actually finding properties like what are its intercepts, or what are its points of discontinuity, things like that. Let's go back to the PowerPoint. All right, so let's keep moving. Let's start off with a simple, here we go. Let's start off with a simple type of rational function when we're talking about these at the start. Those are called inverse variations, all right? So we're just going to stick with inverse variations right now at the start of our unit. First of all, what is an inverse variation? It's the simplest type of rational function, and they take the form, it's shown right here, y equals k times 1 over x, or a simpler way to write it is just y equals k divided by x. K is any non-zero constant, meaning it can be any number, right? Positive or negative, it just can't be 0. And that k value, whatever that number is, it's called your constant of variation. This may sound familiar because back in Q1, we discussed something called direct variation. And inverse variation is kind of the opposite of that, okay? Let's move forward. Inverse variation versus direct variation. If you're looking back in your notes to Q1 and you're looking back on direct variation, you should already see this relationship here, what I'm about to talk about with inverse and direct variation. So first of all, inverse variation. If you were asked to write the equation of an inverse variation, it's in the form y equals k divided by x. However, direct variation, what we talked about in Q1, was y equals k times x. Inverse variation is k divided by x. Direct is k times x. Moving forward. If you solve that equation for k, if you switch the direct or the inverse variation equations to get k by itself, in the inverse variation, the constant of variation is equal to x times y. However, in a direct variation, the constant of variation k is equal to y divided by x. And then the most important things that you guys realize is that third bullet point on this slide. This is the most important thing. With an inverse variation, as x as its magnitude, meaning ignore the sign, just look at the value without the sign. As its magnitude grows larger, the y value or the y magnitude is going to decrease. They're going to go in opposite directions, x and y, opposite directions. However, with a direct variation, x and y, their magnitudes are going to go in the same direction. If one of them is increasing, the other is increasing. If one of them is decreasing, the other is decreasing. Direct variation is, if you were to graph it, it would be a line. It has a slope of k, its constant of variation, and I'm hoping that you remember a direct variation has a y-intercept of 0. In inverse variation, on the other hand, the graph is a curve. You're going to see that shortly, right here. A direct variation, slope of k, y-intercept of 0, and an inverse variation has a downwards sloping curve going on. Which brings us to our first objective, okay? Objective 1, our first problems that we're going to be solving, and the first problems that are going to be on your classwork, we are going to see a table, and we're just going to be asked, does the table represent direct or inverse variation? And if it is one of those, if it is a direct or inverse variation, we're going to write the equation, okay? So you're going to stop seeing my face here, and I'm going to go over to my iPad. Cool. All right. So we are looking at a table of values. I have 4 coordinate points here. And I am simply asked, is this direct or inverse variation? And then if it is one of those, write the equation. I'm going to erase this line here because the first thing that we're going to actually do is we are going to add an extra column to this table because I'm going to do a quick little calculation. If you're thinking this looks familiar, this is the same process as what we did for direct variation. The first thing I'm going to do is I'm going to look at my x and y values. I'm going to observe them. I'm going to see that x in this case is going up and y is going down. So if it is direct or inverse, if it's one of the two, it's going to be inverse. Because x is increasing, y is decreasing. However, we don't know that it's inverse. We have to test that it's inverse. In inverse variation, your k value is x times y. We need to make sure that x times y for each row in this table is exactly the same. It's equal to all the other rows. If it is, then it is an inverse variation. So what are we going to do? We're going to, in this first row, do 6 times 0.25. In the second row, we're going to do 0.5 times 3. In the third, we're going to do 0.75 times 2. In the fourth, we're doing 1 times 1.5. And in the last, we're doing 2 times 0.75. This is just something that you plug into your calculator. And once you do that, I'm hoping that you see, hey, every single one of these multiplication problems comes out to the exact same value, which is 1.5. All of these values are the same. X times y is equal to 1.5 for every point in this function, which means that it is an inverse variation. So it's not direct, it's inverse, right? And since it is an inverse variation, we can write the equation very easily. An inverse variation has the equation y equals k divided by x. What is my k value? Well, it's whatever x times y was equal to for all of the rows in my table. So in this case, our equation is y equals 1.5 divided by x. My constant of variation is 1.5, and this is my equation for that inverse variation. Example 2, let's move forward. Same thing. Does this represent direct or does it represent inverse? Here, I am ignoring my signs. Okay, so I'm just looking at the magnitude. X is going up and y is going up. If x and y are going in the same direction, ignoring the signs, remember, if they are going in the same direction, then this could be a direct variation. In a direct variation, k is not equal to x times y. K is actually equal to y divided by x. So now we go in here and we see, okay, does y divided by x for all of these values, or all of these rows, is it equal to one another? Is it equal to the values in the other rows? That's what we're going to test right now. For this first row, y divided by x is -4/3. -4 divided by 3, or 4 divided by -3, same thing. In this, we have 8 divided by -6. Here we have 12 divided by -9. And lastly, we have 16 divided by -12. Okay, this may not look exactly the same right now. However, each of those fractions, each of those k values, make sure you reduce it, right? 8 over -6 reduces to -4/3. 12 over -9, divide top and bottom by 3, comes out to -4/3. And finally, 16 over -12, divide top and bottom by 4, and we get -4/3. And look at that, just like the last problem, our k value is the same in each row, which means that it is indeed a direct variation. Again, it was a direct variation because our k value of y over x was constant. Because it is a direct variation, the second part of the question asks us to write the equation of this variation. Well, the equation for a direct variation is y equals k times x. Our k value is -4/3. So the equation is y equals -4/3 times x. And that's it. Again, the direct variation problems like this one, you've actually already done the same exact type of problem back in Q1. So this example 2 is totally review. All right, we've actually done this exact same thing before. Moving forward to example 3, one more before we move on to our next objective. All right, so x and y, let's examine them first and see which directions they're going. X is increasing and y is decreasing. Okay, that means that this could be inverse variation because they're going in different directions. In an inverse variation, k is equal to x times y. So I've got to test out what x times y is for each of these rows. If they are the same, the exact same, that means that I will have a inverse variation. Okay, first row, 1 times 5 is 5, easy. Second row, 2 times 2.5 is 5. Okay, it's looking good so far. Third row, 3 times 1.66 repeating. All right, I gotta go to my calculator here. 3 times 1.666 repeating. 4.999999, which is 5. All right, so we're still looking great. Lastly, 4 times 1.5. This is equal to, unfortunately, not 5. It's equal to 6. So here, we looked promising up here. It looked promising. However, this 6 means that we have neither a direct or an inverse variation. Because the k value was not constant in every row. So this is our final answer here. This table represents neither direct nor inverse variation. All right, that's it for objective 1. Let's move forward. Objective 2. We looked at a table. Now we're going to look at inverse variations without a table. What you're going to be doing in objective 2 is find a missing x or y value using inverse variation. You don't need any more notes to do this. You actually have all the notes that you need from this slide right here. Okay, so let's move forward. I'm going back to my iPad and we're going to run through some of these problems. Okay, so objective 2, find the missing variable using inverse variation. Example 1 says, if x and y vary inversely, and x equals 5 when y equals 10, what does x equal when y equals 25? All right, let me examine this here, highlight important parts. First of all, if x and y vary inversely, this right here means that we do have an inverse variation, which means that your k value is x times y. This will always be constant. It will always be equal to the same exact thing. All right. It says x equals 5 when y equals 10. This right here is considered our first case, and then the question is, what does x equal when y equals 25? That's the question. All right, so what we're going to do is we're going to just set up a simple equation. The equation that we're going to set up is this. x1, y1 is equal to x2, y2. The first x and y values multiplied together is equal to the second x and y values multiplied together. It's as easy as that. So our first x and y values, I'm going to do in green, it's written right here, x equals 5 when y equals 10. So that's what x1 and y1 will be. x1 is 5 times y1 is 10. Okay. This is equal to x2 times y2. What are our second x2 and y2 values? Well, that comes from our second part here. It says, what does x equal when y equals 25? So we don't know what x equals. We know that y equals 25 in this case, though. So we are going to keep x2 as x2. And y, we are going to substitute in 25. And then we just solve for x. It's as easy as that. 5 times 10 is 50. Equals 25 x2. And we're trying to solve for x2, so what do we do on both sides? We divide by 25 on both sides. x2 is equal to 50 divided by 25, which means that our x value when y equals 25 is equal to 2. And that is our final answer. Does this make sense? Yes, because 2 times 25 is 50, and 5 times 10 is 50. K equals x times y, your constant of variation always has to be constant. Great. Moving forward. Example 2, the same exact thing. X and y vary inversely. Our first case, it says if x equals 2.5 when y equals 6.25, what does y equal when x equals 2? Oh, that was bad. There we go. What does y equal when x equals 2? All right, so we're going to set up that same exact equation, which says x1, y1 is equal to x2, y2. This is always true for inverse variation. All right, in this problem, what's in green is our first x and y, so we are going to write 2.5 times 6.25 is equal to, now I'm going to purple, x2 is 2, and y2 we don't know. And now we just got to solve for y2. Cool. So on the left-hand side, I'm doing 2.5 times 6.25 in my calculator, and I get 15.625 is equal to 2y2. Divide by 2 on both sides to solve for y2. y2 is equal to 15.625 divided by 2. Doing that in my calculator real quick, and I get 7.8125. I'm going to write that down here. y2 is equal to 7.8125. And that is my final answer. I believe I have one more for you here, and it's a word problem, all right? Thankfully, word problems work exactly the same with this stuff. It's just putting it in a real-world context. So example 3, it says the time it takes to clean your house is inversely proportional, which means the same thing as an inverse variation, okay, to the number of people cleaning. If 2 people are working, it takes 2.5 hours. How long will it take if 3 people are working? Okay, first of all, let's examine our variables, because now we don't just have x and y, right? The time it takes to clean your house is inversely proportional to the number of people cleaning. That first statement tells us the mathematical relationship that we're going to set up. If those two things are inversely proportional, it means that as one thing increases, the other decreases. And this makes sense, right? If more people are cleaning and helping out in your house, the less time that it is going to take overall to get that house clean. So the two things are inversely proportional. Okay, so moving forward, we know that this is going to be an inverse variation. And now we have case one. If 2 people are working, it takes 2.5 hours. I'm going to write that down. 2 people is 2.5 hours. Our second case is how long will it take if 3 people are working? So 3 people equals question mark, right? We don't know how long it'll take. And I should probably make that a variable since this is math class, right? Let's say 3 people equals x. Thankfully, all we have to do is exactly the same thing as what we did before. If we multiply the people times the hours, it should be constant in an inverse variation. So that's what I'm going to do right now. Just going to do this in one color. x1, y1 is equal to x2, y2. Our first case is, in red, 2 people times 2.5 hours is equal to our second case, which is 3 people times x hours. We don't know how long it's going to take for 3 people. So moving forward, 2 times 2.5 is 5. 5 equals 3x. Divide by 3 on both sides. X is equal to 5/3, which is 1.66 hours. And that's our final answer. We found that using the inverse variation, just setting up a simple statement of equality, solving for x. Cool. All right. I believe that is it for this objective. Yes. So let me bring it back to me. And let's keep on moving. So we've got 5 total objectives here. Let's keep going. Our last part of inverse variation, this is our first part of the unit. The last part of wrapping up this intro part with inverse variation is talking about something called combined variation. Okay? Combined variation is when you have both direct and inverse variation in the same exact problem. You've got both relationships going on, multiple variables. So an example of this would be y varies directly with x and inversely with z. You've got direct variation with x and inverse variation with z. That together is called a combined variation. In another example, you could get really fancy with it. You could say y varies directly with x squared and z and inversely with the cube root of s. That can get really tricky. Try to write out those relationships. Maybe pause the video at this point, and I'm going to help you out writing out these examples, what the equations would look like. All right. So that first equation, the first statement, it said y varies directly with x and inversely with z. So for a problem like that, you would have, because it's varying directly with x, you would have y equals k times x. However, inversely with z means that you would have k divided by z. The important thing to remember with combined variation, y'all, is that if you have something varying directly with y, that shows up on the top, as it did with this x, right? That's why it's on top. However, if you are varying inversely with that variable, that variable will show up on the bottom, as it did with the z. So the second example that I stated, you can use those same rules, all right, to write the equation of that combined variation. The second example said y varied directly with x squared and z, which means that we have on top directly, oh, that was wrong. There we go. Directly with x, I'm gonna do that again. Let's make this yellow. Directly with x squared and z. That means that it shows up on top because it's direct variation. And y also varies inversely with the cube root of s. Well, inverse variation would show up in the denominator of the fraction, right? So that's why we have this right here, the cube root of s on the bottom of the fraction. This k value right here is still your constant of variation. It's just now your constant of combined variation. All right, and that is going to bring me to objective 3, which is using combined variation to actually solve problems. So let's move forward here and start solving some problems with combined variation. Example 1 is not a word problem. We're going to get to those later. It says here, y varies directly with a and b and inversely with the square root of c. Find y when a is equal to 5, b is equal to 2, and c is equal to 25. Okay, so y varies directly with a and b. And again, I'm going to go back and do that in yellow to keep it consistent. Directly with a and b, and it varies inversely with the square root of c. Okay, so let's set this up. Y is equal to, we're always going to start it off with a k. It said it varied directly with a and b, so that's going to be multiplying that a and b to the k. Y equals k times a times b. And it varies inversely with the square root of c. If we have inverse variation, that shows up in the denominator of the fraction. So the square root of c will be down here. And now it says, find y when a equals 5, b equals 2, and c equals 25. So we're going to take this equation, and we're just going to plug in those values for a, b, and c and arrive at our answer. Okay? We don't have a value of k, that's going to be all right for right now. Find y when a equals 5, b equals 2, c equals 25. Let's do this. Y is equal to, we don't have a value for k, so that's going to stay k, times a. A is now 5, times b, b is now 2, divided by the square root of c. C is now 25. We simplify this, and then we're done with the problem. Y is equal to 5 times 2 on top is 10k. On the bottom, square root of 25 is 5. 10 divided by 5 is 2, which means, I'll write my final answer over here, y is equal to 2 times k. And that's our final answer for what y is equal to under those circumstances. Let's move forward to some actual word problems where we're set in a context that's in the real world. All right. I'm sorry if my writing is a little sloppy. I'm going to read it out loud as well. If you can't read that, it's kind of hard to write on these iPads. All right, so example 2, it says the number of minutes needed to solve a set of problems varies directly with the number of problems and inversely with the number of people working on the problems. All right, I'll definitely go back and highlight some stuff there. It takes 4 people 36 minutes to solve 18 problems. How long will it take 6 people to solve 42 problems? Okay, let's back it up to the first sentence again. The number of minutes needed to solve a set of problems. How long will it take you to do an assignment? All right. it is going to vary directly with the number of problems. That means that as the number of minutes go up, the number of problems goes up. That makes sense. It takes you longer to do 50 problems than it takes you to do 10 problems, right? So that's direct variation. However, the other part of this, it says that this varies inversely with the number of people working on the problems. This makes sense as well, right? If you have one person working on the problems, it's going to take longer than if you had 10 people working on the same set of problems. I am going to represent these different pieces of information with different variables, okay? This is really important that we do this. T, oops, there we go. T, I'm going to make my variable for the time it takes to solve. In yellow, varies directly with the number of problems. I'm going to make n my number of problems. And then finally, in purple, it said inversely with the number of people working on the problems. I'm going to write P is the number of people. All right, so now I'm going to set up my equation. The time it takes to solve varies directly with the number of problems. So we will have K times P on the top of this fraction. And it varies inversely with the number of people working on the problems. Oh, I'm sorry, I made a mistake. This should be n, right? Sorry about that. So anyways, what I just wrote, K times n, the number of minutes varies directly with the number of problems. That's why n is on top. And it varies inversely with the number of people, which is P. So we're going to put P on the bottom. This is my equation that I start out with. Okay, let's see here. So second sentence, it says it takes 4 people 36 minutes to solve 18 problems. 4 people, that's my P variable. 36 minutes, that's my time variable. To solve 18 problems. Number of problems is yellow. That's my n variable. What I'm going to do is I'm going to plug in 4 for P, 4 for purple, 36 to T, 36 to red, and 18 to yellow, 18 to N. And what this is going to do is it's going to let me solve for my K value. It's going to be able to help me find my constant of variation. So I'm going to do that right now, solve for K, and then it's going to be able to help me find the answer to that last question there. Let me pull up a new slide for us. So our equation was T equals K times N over P. Going back to our original problem here, we were plugging in 4 for P, 36 for T, and 18 for N. Sorry, you guys, this is something that I haven't totally figured out how to do yet, so I gotta keep on going back and forth. You're probably 4 people, 36 minutes, 18 problems. All right, so we're gonna plug these numbers in for their given variables, and then we're going to solve for k. T is time, so 36. I'm going to put right here. K is our constant of variation. We do not know that right now. N is the number of problems, which is 18. And P is the number of people working on the problems, so 4. All right, so how do we solve for K here? First, we're going to multiply by 4 on both sides of the equation. What that's going to do is it's going to cancel out the 4 on bottom. 4 times 36 is 144. And then to solve for k, we're going to divide 144 by 18. So k is equal to 144 divided by 18, which is 8. Our constant of variation is 8 for this problem. Okay, so now our equation, if we were to write this out with our constant of variation plugged in, t is equal to 8 times n over p. This is always true for t, n, and p, that relationship. It's always 8 times n over p equals t. We're almost done. Now going back to our original problem, it says here, I'm going to highlight this in green, okay? It says, how long will it take 6 people to solve 42 problems? How long will it take for 6 people to solve 42 problems? So we don't know the t value. So we're solving for t now. So all we got to do is plug in 6 for p and 42 for n, and then we'll arrive at our answer. T is equal to 8 times n is the number of problems, so 42, divided by p. P is 6, number of people. And plug that into your calculator. 8 times 42 divided by 6. And this gives me 56 minutes. It'll take 6 people 56 minutes to solve 42 problems. That was a doozy, wasn't it? That was definitely a doozy. Let's go back here. If you are looking for an additional example, this is a great one. We're going to go over this as well. If you feel like you don't need this example because you got the previous one, then feel free to skip ahead in the video. But I do want to go over this for the benefit of people who feel a little bit confused still with combined variation. And I'm going to get some water because I've been talking a lot. Give me 30 seconds. All right, I'm back. So, example number 3. It says the number of rabbits varies directly as numbers of squirrels and inversely with the number of raccoons. When there were 10 rabbits and 40 squirrels, there were 2 raccoons. How many raccoons went with 5 rabbits and 20 squirrels? Okay, so another combined variation problem. First of all, number of rabbits varies directly with the number of squirrels. Secondly, it varies inversely with the number of raccoons. So as rabbits increase, squirrels also increase. However, as rabbits increase, raccoons actually decrease because it's an inverse variation. Let's set up this relationship. We are going to say that R, we're going to say that R, the number of rabbits, is equal to K times S, the number of squirrels, divided by, oh shoot, it's another raccoon. I should have thought of that. We're going to say C is equal to raccoons, okay? C is equal to raccoons. Sorry about that. So that's direct variation with squirrels and inverse variation with raccoons. The first case I'm going to highlight in, we're going to highlight in blue. Now we're going to highlight in red. It says there were 10 rabbits and 40 squirrels. There were 2 raccoons. That's case number 1. So we are going to use case number 1 to find what our constant of variation is equal to. We are going to plug that information in. 10 rabbits, 10, equals k times s. S is squirrels, so there were 40 squirrels, divided by c is raccoons, divided by 2. Do some math here. Multiply by 2 on both sides, divide by 40, and we will get k is equal to 0.5, or 1/2. This is what our constant of variation is for this problem. So plugging that in, our equation is now r equals 0.5 times s divided by c. Now, what is the question that is being asked? The question that is being asked is how many raccoons went with 5 rabbits and 20 squirrels? Now, we are going to use this equation, r equals 0.5 times s divided by c, to find the answer to that problem. Again, how many raccoons went with 5 rabbits? So we're going to plug in 5 for r, equals 0.5 times s, which is 20, divided by c. How many raccoons went with 5 rabbits and 20 squirrels? We are solving this equation for c right now. The first thing that you should do is multiply by c on both sides. We will get 5c equals 0.5 times 20. On that right side, 0.5 times 20 is 10. So we have 5c equals 10. And then divide by 5 on both sides, we get c equals 2, which means I had just enough room. But the answer to that question will be 2 raccoons. That was wrong. There were 2 raccoons when there were 5 rabbits and 20 squirrels. All right, cool. Let's go back to our PowerPoint. Back to my face. All right, let's keep going. Got 2 more objectives to do. You guys are doing great. Keep up the good work. Keep up the perseverance. Here we go. Moving on to other types of rational functions. What we were just talking about over objectives 1 through 3 were inverse and then combined variations, right? But inverse variations, those are the simplest type of rational function. So if you want to talk about other types of rational functions, we got to look at those as well. Moving on to other types here. Remember that a rational function is a ratio of 2 polynomials, a fraction with a polynomial on top and a polynomial on bottom. If I give you an equation of a rational function, there are several graphical properties that you need to be able to identify even without the assistance of Desmos. Desmos is really helpful. We're going to use it for sure to confirm our answers, but you need to be able to do it, without as well. So what properties do you need to know? This next slide is definitely something you should have down. When I give you a rational function, these are the things that you should be able to do both through Desmos and by hand. X and Y intercepts, just look where it crosses X, the X-axis, and where it crosses Y. That's easy enough. Number 2 is really important, and it's something that's new. It's called points of discontinuity. There are two types of points of discontinuity. There are non-removable discontinuities, also called vertical asymptotes. And there are holes, which are also called removable discontinuities. Holes and vertical asymptotes are both points of discontinuity. There are also horizontal asymptotes that you need to be able to find. And then if I ask you about the end behavior of a rational function, you need to be able to look at the graph and just determine what that is based off of what you see on Desmos. Remember, I don't have this written down, but it's definitely written in your notes from previous units. An asymptote is a line that your function approaches, but it never actually touches, right? It gets closer and closer to the asymptote, but it never actually touches that asymptote. So what we're going to do now is we're going to look at some rational functions. We are going to determine their properties, and then once we have done that by hand, we are going to confirm that our predictions match what we actually see on the graph. That brings us to objective 4 out of 5, which is find the points of discontinuity of rational functions. We are going to find both vertical asymptotes and holes. They're both points of discontinuity. Holes are called removable discontinuities, and vertical asymptotes are called non-removable discontinuities. If you're wondering what do these look like, you will see several examples of what these look like on Desmos shortly once we actually get to some problems. Okay. There are steps for finding these. If you want to find points of discontinuity, both holes and vertical asymptotes, this is what you do right here. Please make sure you write this down, all right? We're going to factor the top and bottom of the fraction. You always have to factor if you can. This goes back to our quadratics unit. If you don't know how to factor, you got to make sure you're watching videos on Khan Academy or asking me for help throughout this week on Teams, because factoring is not the focus of this conversation that we're about to have as I'm presenting these problems. You got to be confident in factoring at this point. Then you set each factor in the denominator equal to 0, and those are going to be your points of discontinuity. You may have 1 or 2 or 3 or 4 points of discontinuity. X equals something. And then each point of discontinuity is either a hole or a vertical asymptote. If the factor that solution came from cancels out with the top, it's a hole. If it doesn't cancel out with the top, it's a vertical asymptote. So now that you know the steps, we're going to actually go ahead and look at some problems. All right. Objective 4, example 1. Find the points of discontinuity for y equals 1 over x squared plus x minus 20. We're going to do this by hand first, and then we're going to look at Desmos to make sure that we got it right. First of all, step 1 is we factor the top and bottom. The top of our rational function right here, we can't factor that. It's just a 1. However, x squared plus x minus 20, we definitely can factor that, right? What two numbers multiply to give me negative 20 and add to get 1? That's the sort of question that you should be asking here. So we're going to factor the bottom, and we will get y equals 1 over x plus 5 times x minus 4. So we factored the bottom. We couldn't factor the top. If we could, we would need to, but we couldn't in this case. Okay, so now step 2 is we set the bottom factors equal to 0. X plus 5 and x minus 4, set them both equal to 0. And solve for x. Subtract 5 from both sides here, we get x equals negative 5. Add 4 to both sides here, we get x equals 4. These are my points of discontinuity. But you have to determine in step 3 whether they are a hole or whether they are a vertical asymptote. To determine that, you just simply say, do they cancel out with the top? Does x plus 5 cancel out with the top? No, there is not an x plus 5 up here. Does x minus 4 cancel out with the top? No. You would see x minus 4 up here if it did. So both of these don't cancel out, which means that both x equals negative 5 and x equals 4 are both vertical asymptotes. And I just call these for short VA. All right? So the answer to this problem is we have a VA at x equals negative 5, and we have a VA vertical asymptote at x equals 4. These are my points of discontinuity for this problem. Now, I don't want to just say that and then be like, believe me, it's true, right? Let's actually go to Desmos and look to see if our graph actually has vertical asymptotes at those locations. Where's Desmos? All right, here we go. I'm going to take that silly graph away, and we're going to type in our function, y equals 1 divided by x squared plus x minus 20. Here's our graph. Looks kind of strange for sure, right? But now let's type in our vertical asymptotes and see if it lines up with our graph. Our first vertical asymptote was x is equal to negative 5. You can see that in red, and it's true. Our graph does have a vertical asymptote. The black function gets closer and closer to that red asymptote, but it never actually touches it. I'm zooming in right now. It never actually touches it. Our second vertical asymptote was at x equals 4. Let's plot that in blue, and you can see that this works out as well. I'm going to zoom in over here. At the line x equals 4, a vertical line, our function gets closer and closer and closer to that blue line, but it never actually touches it. And I can zoom in, you can see it never actually touches. So to sum it up, right, we have two vertical asymptotes, x equals negative 5 and x equals 4. Let's do another one. All right. This problem we are asked to do the same thing. Step number 1, what do we got to do? You got to do it every time if you can to factor the top and bottom. Oops. Factor the top, we can't. So we keep it as x minus 3. Factor the bottom, though, we definitely can. That is a... Oh, and I made a mistake when I wrote this problem down. Please make sure you change this, okay, you guys? Please make sure you change that to an x. So it should read x cubed plus 4x squared minus 21x. Okay. So I'm going to factor the bottom. I'm going to do this off to the side real quick. This is a cubic, which we can't factor unless we take out a GCF. Thankfully, we can take out a GCF of x here, so I'm going to do that. X goes into each of these terms. So I'm going to take it outside of parentheses, and then I'm going to write the resulting expression inside x squared plus 4x minus 21. And now, what's inside, what I just highlighted in yellow, we can factor this by asking what two numbers multiply to give me negative 21 and add to give me 4. And those two numbers will be positive 7 and negative 3. 7 times negative 3 is negative 21. 7 plus negative 3 is 4. So that's what the bottom of my expression factors out to, which I'm going to write up there where we were working before in red. X times x plus 7 times x minus 3. Great. Now, I set each factor in step 2 equal to 0 on the bottom. So I'm going to set x equal to 0. That's one of my vertical discontinuity, I'm sorry, not vertical, points of discontinuity, x equals 0. X plus 7 equals 0, that's going to give me x equals -7. And then finally, x minus 3, that's going to give me x equals +3 when I set that equal to 0 and solve for x. Next, finally, I am going to check to see whether each solution here, whether each point of discontinuity is a whole or a vertical asymptote. First one, x. Oops. Does that cancel out with the top? No. If you're wondering, I see an x right here. I'm sorry, y'all, that's at x minus 3. The factor is x minus 3. So we do not see an x just by itself up there as a factor, which means that this does not cancel out. So x equals 0 will be a vertical asymptote. Okay, next. X plus 7. Does it cancel out with the top? No, there is not an x plus 7 up there, which means that x equals -7 is a vertical asymptote. However, look at this, y'all. Our last one, x minus 3. Does that cancel out with the top? Yes, it does, because we have exactly x minus 3 up there as well. If those cancel out, we actually don't have a vertical asymptote at that point. We have a hole. And this is our first hole that we have. You're going to see what that looks like shortly on Desmos. So our final solution to this problem is we would say we have a vertical asymptote at x equals 0 and x equals -7, but we have a hole at x equals 3. All right, I'm going to go to Desmos and we're going to plot those things now. First, I'm going to plot the original function, y equals x minus 3 divided by x cubed plus 4x squared minus 21x. Next, I'm going to plot my two vertical asymptotes. They should appear right here and right here, if we did this correctly. My answers that I got for my asymptotes were x equals 0, that looks good, and x equals -7. That looks good. You can see that they line up perfectly with our graph. Those are the asymptotes that we should expect. Okay, great. Now, we can't plot a hole on Desmos, so we're just going to look for it. Our answer from before, it said that we were supposed to have a hole at x equals 3. Oops. So going back to Desmos, if we scroll over to where x equals 3 on our graph right here, and I click on this point, you aren't going to see the hole pop up. Actually, you will. Look at that. There it is. At x equals 3, our function is actually undefined at this point. Why does this happen? Why does this occur? The reason being, y'all, is that you cannot divide by 0. Going back to this problem, if any of those factors on the bottom were equal to 0, then it would be impossible to evaluate what that's equal to because it's impossible to divide by 0. That's why these points of discontinuities occur. You have vertical asymptotes and you have holes because you can't divide by 0. And that basically sums up objective 4. So let's move forward here to objective 5. You guys are doing great. This is our last objective before we talk about just a little bit of the Khan Academy homework, okay? Let's bring it back to this. All right. Objective number 5 is this. Find horizontal asymptotes of rational functions. I told you that you needed to find the points of discontinuity, which are vertical asymptotes and holes, but you also need to be able to find horizontal asymptotes, right? This is a lot easier to do and it takes a lot less time. We're going to jump through a couple of examples, but first please write this down. To find horizontal asymptotes, you need to compare degrees of the top and bottom. You don't need to factor it all. You don't need to do any calculations. You simply need to look at the degree of the top and the degree of the bottom and compare them. If the top degree is larger, there's no horizontal asymptote. If the bottom degree is larger, then the horizontal asymptote is at x equals 0. And then finally, the trickiest case, we're going to go through this last, but it's not that hard. It's trickier than the others. If your top and your bottom degree are equal, then you actually have to divide leading coefficients to get your horizontal asymptote. And I'll show you an example of what that specifically looks like. Back to problem solving. I'm not going to pull up Desmos for this one, just because they all go pretty quick. All right, but you can definitely pull it up on Desmos just so you can see it, the horizontal asymptotes on your own. All right, find horizontal asymptotes for this function, y equals 2x over x squared minus 5x minus 20. We are just comparing the degrees of the top and the bottom. What is the degree of the top? Well, that's 2x to the first power. Remember, degree is the highest exponent, so the degree of the top is 1. Okay. What is the degree of the bottom? Well, it's x squared minus 5x minus 20. The degree of the bottom, the highest exponent, is 2, which means that the bottom degree is larger. What does this mean? Consult your notes, go back to this PowerPoint slide. If the bottom degree is larger than the top degree, that means that we have a horizontal asymptote at x equals 0. And it's as simple as that. I changed my mind. I do want to show you one example of what this horizontal asymptote looks like. Okay, so I'm going to go back here to Desmos and I'm going to type this in. Y equals 2x divided by x squared minus 5x minus 20. The function is in red. I got to zoom out here. Oops. Cool. All right, so this is a very zoomed out version. But if I plot the line y equals 0, you can see my horizontal asymptote here. My red function gets closer and closer to the blue line, but it never actually touches it. So this indeed is what you should see. All right, I made a mistake when I wrote this originally. Please change this. Our horizontal asymptote is not at an x value, it's at a y value because it's a horizontal line. So please change that to y equals 0. Or our horizontal asymptote is at y equals 0. Moving on to example 2. Y equals 3x to the fourth minus 22x over 5x to the third minus 17. Compare the degrees of the top and the bottom. The top degree is 4, 3x to the fourth. The bottom degree is 3, which means that the top is greater than the bottom degree. What does this mean? Consult your notes again, consult that slide. If the top degree is greater than the bottom degree, that means that there is no horizontal asymptote. So please write that. There is no horizontal asymptote. Example 3 is going to go over that last case where the degrees are the exact same. All right, so here the top degree is 2 and the bottom degree is also 2, which means that the degrees are equal. What it said on the PowerPoint slide is to divide the leading coefficients to find your horizontal asymptote, which means that the first two numbers that you see on top and bottom, the 3 and the 2, you're just going to divide those, and that's going to be your horizontal asymptote. All right, so our horizontal asymptote for this problem is y equals 3 divided by 2. Y equals 3/2. And that's it. There is one last thing that I want to discuss with you. What we've discussed in the PowerPoint so far will definitely help you with all of the classwork and all of the Khan Academy, but there is one additional thing on the Khan Academy homework assignment that isn't covered in this PowerPoint presentation. So that's what I want to go over right now. And that KA objective is how to find the inverse of a rational function. So I'm going to go over one example with you of that process right now, and then we will be done. If you want to find the inverse of a rational function, we are going to follow the same steps as what you did last week when you were finding inverses. But there is this one little tricky step that pops up, and I want to make sure that you understand how to do that, okay? So first of all, when we are finding the inverse of a function like this, our first step is we are going to switch x and y, and that's what I'm going to do right now. Y becomes x, and x becomes y. So now we have x equals 5 plus y over 4 minus 2y. At this point, what we are going to do, and this is where people get stuck, they're like, how do I solve for y? Because step 2 is get y by itself, and it's a lot harder to do that here, right? Feel free to pause the video and try it out on your own before I tell you what to do. But if you're looking for that help, here it is. What we are going to do at this point is we are going to multiply by the denominator on both sides. That's going to bring this 4 minus 2y over to the left, and it's going to cancel it out on the right. Then, when you have this equation without a fraction, you're going to distribute the x on the left side. So we will have x times 4 is 4x, and x times negative 2y is negative 2xy. I'm going to bring this over here now, okay? Just going to rewrite it. 4x minus 2xy is equal to 5 plus y. Excuse me. Next, you want to get anything with a y on one side of the equation and anything without on the other side of the equation. All right, so what I'm going to do is I'm going to add 2xy to both sides. And I'm going to subtract 5 from both sides. This gives me 4x minus 5 is equal to y plus 2xy. Why did I do this? Because I want the y's on one side. I have that over here. These have y's, and these do not. And this is where it gets a little bit tricky. If you want to solve for y, if you want to get y by itself, you're going to actually have to take out a GCF of y on this right side of the equation. If you take out a y from this expression highlighted in yellow, y times what gives you y, y times 1 gives you y. And then y times what gives you 2xy, y times 2x gives you y. This is going to stay the same on the left. And then finally, if you're trying to solve for y, you're going to divide by that 1 plus 2x on both sides now. And it's going to go back over to the left. So the inverse of a rational function is another rational function. In this case, the inverse, I'm going to put that apostrophe there, y apostrophe is the inverse of y. This is equal to 4x minus 5 over 1 plus 2x. So that's just one example to get you started on that Khan Academy objective. If you're having more trouble with those problems, then please make sure you're reaching out to me throughout the week. All right, let's close this up. All right, so that is it as far as lecture for this week goes. You have everything that you need to succeed moving forward. But if you have questions, I totally understand. It's a lot to be thrown at once, right? So what you should be doing now is you should be starting your classwork assignment in your Khan Academy. You should be taking note of any questions that you have. Please ask them during video chats. If you're not available to ask a question during a video chat, and remember, you can show up to anyone that you want. Please just post your question in the discussion channel, and I will answer it right away from 8 to 2:30. I'm on Teams all day long from 8 to 2:30, Monday through Friday. I can answer questions, but classmates can also answer questions on those discussion channels. Video chats will be at the same time this week, at 10:15 for my 2nd and 6th period classes. What was it? 11:45 for my 3A and 7B classes, and then 1:45 for my 4A and 8B classes. You can show up to multiple video chats if you need, multiple times where you need help. Feel free to log on to every one if you're that type of person. I hope you all have a great week. Reach out to me for questions. Again, this is the first week of Q4, so start it off well. See you guys later.